K, we talked about the fact that some of them are done with molarity and some of them are gases. So are the K's interchangeable? No. Yes. No. They're not interchangeable, but you can interact them by converting one to the other. It is a known conversion, and I'll show you how we get it, etc. So, for example, this is two gases. We could actually present the values in molarity, and then we'd be done. Or we could present them in pressure. So notice that this one is raised to the first power, as is this one. This one is raised to the second one, as is this one. The P stands for pressure. So, how do they interrelate? Well, you just have to follow along on this. So, follow with me. Back in 1211, you did the ideal gas law. PV equals nRT. Well, if you rearrange to put the V over the N is moles, so moles over liters is equal to molarity. Well, remember we're talking about molarity within the brackets. So if we rearrange it, this is molarity of A, RT. So if we rearrange to find the concentration of A, it is the pressure of A over RT. Now, a couple things I want to point out. Temperature has to be in Kelvin, and R is the gas constant. And the gas constant we'll use is 0.0820, well, what I said, not what I wrote, 0.8206 liter atmospheres per mole K. Mole K. Okay, so that would be our values. They're all on our equation sheet, so we're good on that. It's not a big deal. So let me walk you through. Don't freak out. You don't have to reproduce this. I just need you to follow it. If we start here with our Kc, and we convert the concentrations, we know the concentrations can be related to the pressure of each component divided by RT. So if we take it here and keep rearranging until we get just the species times all of basically the constants. Now, temperature is not constant, but it'd be constant in this case because we're all in the same container. Then we end up with a Kp times 1 over RT and the exponent. So we'll start again at that point. So now we would have the Kc is equal to the Kp times this. And if we bring it together, this would be the moles of product, and this is the moles of the reactant. So the net effect is if we rearrange it to where we've got we're solving for Kp instead of Kc. Okay, so Kp is equal to Kc times RT product over RT reactant. Then what that ends up is being delta T. Because remember, delta T is product minus reactant, final minus initial, always. So in this case, we're looking at moles of gases in the product and the moles of gases in the reactant. Now the trick is if you get a negative, you get a negative. If you get a positive, you get a positive. So what this allows us to do is take a Kc, a K based upon concentration, and convert it to a K based upon pressure, or a K based upon pressure and convert it to a K K in concentration. Okay, so the first step is remember we said that Kp equals Kc RT delta N. And I'm going to tell you right now, the two hardest things to this is the delta N and doing the RT first before you do the delta N to it. So let's find the delta N. So what we're basically going to do is find the number of moles of reactants and the moles of products. So we have 4 moles here, 5 moles here, so we have 9 moles on the reactant side, and we have 10 on the product side. So delta N will be 10 because it's products minus reactants. So delta N would be equal to 1 for this one. All right, so let's go down here and look at the delta N here. So if we look at the reactant side, how many moles do we have? 2. No. 0. What? Wait, no, we got 2 moles there. Yes, but they're solid. Look at the reactant side. How many moles of gases do you have? None. So here, over here on this side, we have 2, but we can't count those because those are solid. So we have 4 gases here and 1 gas here, so we have 5. So 5 minus 0 is 5. So delta N for this reaction is 5. So when you go to calculate delta N, be careful because it is truly a function of the states. Okay? So let's work a problem. The Kp for this reaction at 120 degrees C is given. What is the Kc for the reaction? Okay. Now, you can do this in any order that you want. However, I'm kind of annoying. I go ahead and say, oh, look, there's a temperature. Let's go ahead and convert it. So if I add 273.15 to it, I'm going to end up with 445.15 K. So there's my temperature. So my temperature is 445.15 K because we added 273.15 to it. Okay, so that's my one side. My formula is Kp is equal to Kc RT delta N. And I'm not going to lie, I always put the Kc and the Kp in the wrong part, so I have to look at the formula. Okay, so let's go ahead and find the delta N. How many moles are on the product side? 2 and 2, so 4. No, these fall out because they're pure liquid, so that's 2. On the reactant side, we have 2 and 3. They're both gases, so we'd have 5. So our value for delta N is negative 3. Okay? So we know that the Kp is 0.0215. We're looking for our Kc, and our R is 0.08206. Liter atmospheres per mole K. Remember, that's a constant. Times 445.15 K, all raised to the negative 3. So be very careful when you put that one in your calculator because that's the problem child. So we end up with 0.0215 is equal to Kc times 36.529009. Again, I'd let the calculator carry that. So to the negative 3, so 0.0215 is equal to Kc times 2.0515699 times 10 to the minus 5th. So Kc then is equal to 1047.9779. Now, how many digits? I will tell you how many digits to report it to on the exam. Okay? But that was a simple Kp to Kc. Now, on the next one, you're given a Kc, and the question is Kc equal to Kp? If Kp is not equal to Kc, what is Kp? 5. So, what it really boils down to is what is delta N? Delta N on the product side is 2 because the liquid is not going to count. On the reactant side, it's 9. It says negative 7. If delta N is equal to 0, then Kc equals Kp. But if it's not equal to 0, no. So, what we're looking for is Kp. We're given Kc, and I'll go ahead and write the formula. So Kc is 1.83 times 10 to the 3 times 0.08206 liter atmospheres per mole K. Do you have to put in the units? No, but I always do because A, it makes me feel better, and B, it makes me make sure that I'm in Kelvin, and this one was given in Kelvin, and we're going to raise it to the 7th. So that's 1.83 times 10 to the 3rd times 164.12 raised to the negative 7th. That's 1.83 times 10 to the 3rd times 3.1179521 times 10 to the negative 16. Wow. So my KP value is going to come out equal to 5.7058523 times 10 to the negative 13. And I would tell you the number of significant figures that I want, but if I have 4 places after the decimal, that's what KP is equal to. All right? So those problems are relatively simple, and you will definitely have one on the exam. You might have the simple delta n first, or you might have the whole problem. But that's your first equilibrium conversion, KC to KP, and vice versa.